So this is the 43rd session on relative velocity. So in this session we'll discuss relative velocity problems on case 1 of the class of problems stated in session 42. Okay. So if you don't go through this session directly, you first see the session 42, read what case 1, case 2, case 3, case 4 is all about, and then you come to this video. So in this we'll discuss the case 1 questions on relative velocity for mutually translating frame as was stated in session 42. Fine. So I'll write down the question. Fine. I'll write down the question. So raindrops are falling at a speed of 4 km per hour with respect to ground, G for ground, at an angle of 30 degree with a downward vertical. At an angle of 30 degree with the downward vertical to the left. At an angle of 30 degree with the downward vertical to the left. A person holding an umbrella runs horizontally to the right. At a speed of 3 km per hour with respect to ground. Okay. Find two things we have to find again. First, speed of raindrop as seen by person. With respect to man. Second, at what angle with the downward vertical should the person hold the umbrella axis to protect himself from the raindrop in best possible way. Okay, fine. These are two things which have to be found out. Fine. Yes, I'll grab it. Okay. So first of all, what we do, we find the object under consideration, the frames under consideration. Object under consideration is raindrop, which we denote by R say. Instead of frame M, we have man. Man is frame M, which we denote by M say. And for frame F, we have ground, which is denoted by G say. Now what we do, we write down the vector equation for translating frames. VRG is equal to VRM plus VMG. Alright. Now VRG is given to us completely known, 4 km per hour at an angle of 30 degree to the left of the downward vertical. VMG is also completely known, VRG is known, 4 km per hour at an angle of 30 degree with the downward vertical to the left. VMG is also known, 3 km per hour to the right with respect to ground, and nothing is specified about this. So it's again a problem of case 1. So now we have to determine two things. First, we have to find the speed of raindrop as seen by person. That is, we have to find the magnitude of VRM. VRM is the magnitude of velocity of raindrop as seen by the person. That is magnitude of the vector VRM, which is nothing but before finding this, we can solve this vector equation. From this vector equation, we see that VRM is equal to VRG minus VMG. Alright, fine. So now we have to find the magnitude of VRM. Alright. Now either we apply the vector formula, or we can draw the diagram and then solve. That also we can do. I'll draw the diagram, okay. So this will be written as VRG plus minus of what? VMG. Reverse and add. Now VRG is how much? 4 km per hour at an angle of 30 degree to the left of the downward vertical. So this is the downward vertical. This one is downward vertical. So raindrop VRG is coming in this direction. This is VRG. Its magnitude is given to be 4 km per hour at an angle of 30 degree to the left of the downward vertical. Now VMG is 3 km per hour rightward. So minus VMG will be reverse of VMG, 3 km per hour to the left. Now we have to add these two vectors in parallelogram method. We parallelly shift any one of these two vectors so that the tails coincide. So this is minus VMG. This is just 3 km per hour. With these two adjacent sides, we complete the parallelogram. Parallelogram has been completed. Fine. Now the diagonal of this parallelogram through the common tail of these two vectors. This is the vector VRM. Alright. This is 30 degree. This is 90 degree. This angle is how much? 60 degree. This angle is equal to how much? Tell me. 60 degree angle it is. Fine. Now we have to know VRM. Now to VRM, we apply the parallelogram law of vector addition. Alright. I'll rub this first column, okay? So from parallelogram law of vector addition, VRM is nothing but root under 3 square plus 4 square plus 2 into 3 into 4 into cos of 60 degree. So this becomes equal to root under 3 square plus 4 square is 25 plus 2 into 3 into 4, 12, cos 60 is half, 2 goes away, root 37 kilometer per hour. That is the answer to the first part of the question. Alright. So this is the answer to the first part of the question. Speed of raindrop as seen by the person will be equal to root under 37 km per hour. Fine. This is the first thing which has been found. Now we have been asked to find at what angle with the downward vertical should the person hold the umbrella axis so as to protect himself from the raindrop in the best possible way. Now in order that the person protects himself from the raindrop in the best possible way, he should align the umbrella axis along the direction of velocity of raindrop as seen by the person. Suppose the person sees that raindrops are coming like this. Person observes that raindrop is coming to him along this direction. So he should hold the umbrella axis along this direction. If he observes that raindrops are falling vertically downward with respect to him, then he should hold the umbrella axis like this. If he sees that raindrops are coming with respect to person, raindrops are coming like this, he should hold the umbrella axis in this way. Alright? Then he'll protect himself from the raindrops in the best possible way. So in this case, the person should hold the umbrella axis along the direction of VRM to protect himself from the raindrop in the best possible way. So in part B of the question, person should hold the umbrella axis along VRM to protect himself from the raindrop in the best possible way. Now suppose this VRM makes an angle of theta with the downward vertical. This theta we have to find out. Alright. Now what we do, we extend this backward, okay. So this is a right angle triangle. You can see this is a right angle triangle. This is a right angle triangle. This is the hypotenuse VRM. This is 3. This is equal to 4. Alright. So if we know this side and this side, then tan theta will be this by this. Now this is 4. This is 30 degree. This is right angle. So this side becomes, in this right angle triangle, this side becomes 4 cos 30 degree. 4 root 3 by 2. 2 root 3 km per hour, this height. Now we have to know, due to determine theta, we have to know this length. Now this length is 3. This length is also 3. Parallelogram law of opposite sides of parallelogram, they are equal. Now this is 30 degree. This is 4. So this is how much? This will be how much, tell me? This will be equal to 4 sine 30 degree. This will be equal to 4 sine 30 degree. Sine 30 degree is 1 by 2. 4 by 2 is 2 km per hour. Okay. So now what do you see? Tan theta becomes this side by this side, this right angle triangle. Now this side becomes 3 plus 2, 5, and this is 2 root 3. So tan theta becomes 3 plus 2, 5 upon 2 root 3. 5 by 2 root 3. So theta should be equal to tan inverse 5 by 2 root 3. That is therefore the required answer. This is not a well-known angle, so you leave it as such. Okay. So in order to protect himself from the raindrop in the best possible way, the person may hold his umbrella at an angle of theta with a downward vertical, where tan theta is equal to 5 by 2 root 3, or theta is equal to tan inverse 5 by 2 root 3. That is the required value of theta, so that the person protects himself from the raindrops in the best possible way. Fine. So this I have discussed one question. Okay. This was the second problem on case 1. Okay. Now in this session I will take up one more problem on relative velocity of this case 1. Alright. I will rub it. Okay. Now we take another problem on case 2 of this in this video. Now this problem is similar to first problem with the only difference that in the first problem which we discussed just now, person was running to the right. Now suppose the person runs to the left and remaining data is same. To solve the previous question, of this video, with the only difference that person runs to the left, not rightward but leftward with respect to ground. with respect to ground. And the remaining data is as it is. No change in the data. Okay. So now again we have to tell two things we have to find. Magnitude of VRM, vector VRM, and angle which the person should hold the umbrella axis with a downward vertical so as to protect himself from the raindrop in the best possible way. So now again we write down the vector equation. So R, again object under consideration is raindrop denoted by R. Instead of frame M we have man frame which is denoted by M. Instead of F frame we have ground frame which is denoted by G. So we write down the vector equation again. VRG is equal to VRM plus VMG. This is how we write. So from this we see that complete information of VRG is given. VMG also complete information is given. And we have to find the magnitude and direction of VRM. So it's again the problem of case 1, you can see it. So directly proceed to the rule for case 1. Alright. So now again we have to tell what is the speed of raindrop as seen by the person, and what angle should he hold the umbrella axis so as to protect himself from the raindrop in the best possible way. So for it is better if you draw the vector diagram. Okay. So now VRG and VMG are known, so we solve this vector equation. So VRM is just equal to VRG minus VMG. This is just equal to VRG plus minus of VMG. This is how we write. Okay. Now VRG, we draw the arrow for vector VRG. VRG is this one. This is VRG. 4 km per hour at an angle of 30 degree with the downward vertical to the left of it. Now VMG is what? 3 km per hour to the left. So minus VMG is 3 km per hour to the right. So this vector is minus VMG, that is 3 km per hour. Fine. Alright. Now what we do with these two adjacent side, we complete the parallelogram. With these two adjacent side, we complete the parallelogram. Okay, fine. So we complete the parallelogram now with this one. Okay, so this is 4 km per hour. This is 3 km per hour. This is 30 degree. All right, is it clear? So now VRM is, we will adjust it slightly more. See, while one thing you have to note in this problem, see this is 4, this angle, if you draw a right angle, drop a normal here, this is 4 sin 32, 2 km per hour. This is 3, this is more than this. So resultant of these two will not be in this sense but in this way. Is it clear what I have said? See, I am saying if you drop a normal from here, this is a right angle, this is 30 degree right angle, so this becomes 4 sin 30 degree, that is 2 km per hour. Okay. Now VRG, VRM is the vector sum of these two. So VRM will pass through the common tail of these two. VRM can be this side also, this side also. But if VRM is this side, then this is 3, this is 2. So this is more than this. So VRM should not be in this side, but it should be this side. Head of arrow VRM should be to the right of this perpendicular, not to this side but that side, because this 3 is more than 4 sin 30 degree. Alright. So with these two adjacent side, we complete the parallelogram. Okay. And diagonal through the common tail of these two, this one. This is VRM. Is it clear what I have said just now? I was trying to say that VRM will be like this, not in this way, because 3 is more than 4 sin 30 degree. That's why. Alright. So this is VRM. It makes an angle of 5 with the vertical. Now we have to first find the value of VRM. Alright. VRM we have to determine. Now this is 30. This is 90 degree. This dotted right angle. So VRM from parallelogram law of vector addition is root under 3 square plus 4 square plus 2 into 3 into 4 into cos 90 plus 30, cos 120 degree. Cos 120 degree is known to be minus half. So this is equal to 3 square plus 4 square 25, and this is 12 into 2 24 into cos 120 is minus half. So root 25 minus 12, so it becomes equal to root 13 kilometer per hour. This is the answer to first part of the question. Fine. So answer to first part of the question is root 13 kilometer per hour. That is the answer to the first part of the question. Alright. I'll wrap the first column. Fine. Now we have to find the angle which the person should hold the umbrella axis with the vertical so as to protect himself from the raindrop in best possible way. As I just discussed in the previous question of this video, 43rd video, person should hold the umbrella axis along VRM to protect himself from the raindrop in the best possible way. Now it is seen from this diagram that VRM makes an angle of phi with the downward vertical to the right of it. So you have to find phi. So tan phi is just equal to, see this is a right angle triangle. See this right angle triangle, okay? Tan phi becomes this by this. Now this is 4, this is 30 degrees. So this, in this right angle triangle, this side will be how much? This side will be equal to 4 cos 30 degree. 4 cos 30 degree, 4 root 3 by 2. 2 root 3 kilometer per hour. So this becomes 2 root 3 kilometer per hour. Alright. Now we have to determine this. This length is this length minus this length. This is 3, this is also 3, parallelogram, and this is 4, this is 30 degree, this is 4 sin 30 degree. So this angle becomes 4 sin 30 degree, that is 2 km per hour, and this is 3, this is also complete 3. So this length will be how much? This length will be 1 km per hour. So tan phi becomes 1 by this. So tan phi written as 1 by what? It will be written 1 by 2 root 3. So phi should be equal to tan inverse 1 by 2 root 3. It is therefore the required answer. Alright. So in order to protect himself from the raindrop in the best possible way, the person should hold the umbrella axis at an angle of phi to the right of the downward vertical. The tan phi is equal to 1 by 2 root 3. That is phi is equal to tan inverse 1 by 2 root 3. And this is not a well-known angle, so you can leave it as it is, because to know the exact data you have to consult the table of trigonometry. Okay. So you leave it like this, it's alright. Okay. So this problem is also finished. Okay. So in this 43rd video, I have discussed 2 more problems, okay? And 42nd video, I discussed first problem on case 1. And in 43rd video, I discussed 2 more problems on case 1. And in 44th and 45th video also, I will take up 2 more problems on case 1. Then I will pass over to case 2. Fine? I close it here itself. Alright?